radiation under Unit 4. And in this unit, we are going to talk about Fourier transform infrared spectroscopy. Okay, so at the end of the session, you should be able to learn more about what FTIR is about. Okay, so Fourier transform infrared spectroscopy is a technique used to obtain an infrared spectrum of absorption or emission of a solid, liquid, or a gas. Now, some IR instruments used to have a monochromator as the key device that is used to disperse and separate the broad spectrum of the IR radiation into individual narrow IR frequencies. However, the Fourier transform infrared spectroscopy uses an interferometer, right? So, I want to use the laser. Okay, yeah. So, some IR instruments were using the monochromator to disperse the band of the frequency or to separate the broad spectrum of the IR radiation into individual narrow IR frequencies. But so this is the monochromator here. This is the monochromator here that is used to disperse or scatter the broad wavelength into individual narrow IR frequencies. However, the FTIR uses an interferometer instead of the monochromator. So that's typically the main difference that comes with it. And the output data from an IR spectrum is, an FTIR is stored in digital form in a computer memory and can be manipulated afterwards. Okay, so this is a typical schematic of the interferometer. So the interferometer consists of one fixed mirror, this is the fixed mirror, and then one movable mirror. So this is the movable mirror, and then of course a beam splitter here. Now, one half of the radiation is reflected by the beam splitter, strikes the fixed mirror, and is reflected back to the detector. And the other one half of the radiation is transmitted by the beam splitter to the movable mirror and is reflected back to the detector. So that's the purpose of the beam splitter, splitting the IR source into two different forms which enters the detector. But of course, it passes through the sample before reaching the detector. Now, the advantages of FTIR can be enormous, since the data is stored on a computer instead of taking one scan of the sample. Multiple scans can be taken at a time. So in FTIR, you can run your sample over and over. Right. So these are pre-lab questions you need to address or look at before you perform your experiment. Now, for FTIR analysis, infrared radiation comprising a range of frequency is directed at the sample, right? And the detector reads the intensity of the transmitted radiation at all frequencies scanned, and the absorbance or transmitter's value are calculated and recorded by the software. So you have your electromagnetic spectrum here, and then you have the range for your IR region here. Now these values are mostly before running your sample, you have to make sure that you run a background test, and this background has to be subtracted so that you don't end up assuming that some of these absorbances are from a sample, whereas they are just background absorbances. So in your experiment, you are going to be given an unknown organic compound, and then you add the spectra to it, and then you are supposed to tell us what kind of organic compound the spectra represents. So first of all, if your sample is a liquid, you run the background spectrum without any solvent. So that is the background spectrum running. So you run your background spectrum with no solvent, and then when you add your solvent, then you run it again. So you pour a few drops of your sample liquid into a Schraub plate crystal. That is the cell we've been talking about, and then you use a non-adhesive tissue to clean it if there are any spill off, and then you dry the surface with a few drops of ethanol in the clean tissue. Then you click sample measurement to Now, if your sample is a solid, you've talked about how to prepare your solid samples. So you of course run the background spectrum without the sample to make sure that anything you are reading is not as a result of the background noise, but just your sample. So after running your background spectrum, you subtract that background spectrum from the, one you ran when your sample is added. So just as we've talked about, you prepare your solid sample, you add it to however you prepared your solid sample, whether you use the potassium bromide pellet approach or the NEOMO approach, or you just mix it with DCM, whichever way you prepare it, you also run that as well, and then you get your spectrum. So these are some important notes. You have to make sure that you clean all the tools and the sample crystal with ethanol before sample preparation. Then you have to use proper sampling tools, tweezers, and a spatula to avoid or any other um, contamination. There are quite a number of these things you have to make sure you 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 do them before and after running your sample. Now, each group will have one unknown to identify. So a multiple choice selection of possible substances or molecules will be given, and you pick the most likely match for each sample. So for the report, you write down the structures of all possible compounds in the list that will be given to you. And based on these structures and then the actual spectrum that is obtained, we discuss in detail for each structure why it is or why it is not the correct identity of the unknown. So for group one, this is your spectrum. So assuming after running the FTIR for your sample, this spectrum was obtained, select from the list of compounds which most likely has the spectrum below. So you have four compounds to to select, right? So one of these compounds has this spectrum. So you have to make sure you use what has been taught to identify the spectrum here. So this is for group two. Now this slide is just to help you show the kind of stretches that you have at certain wave numbers, right? So we have carbon, carbon triple bond, carbon nitrogen triple bond here. You have carbon oxygen stretches around 1650 to 1800. We have the OH stretching at 3200 to 3400 per centimeter. So this is just to help you in your